Welcome everybody to the Asia Pacific PDE seminar. Our guest today is Professor Frank from Caltech University in Pasadena and also professor at LMU in Munich. Professor Frank, he defended his PhD in 2007 at the Royal Institute of Technology in Stockholm under the supervision of Ari Laptev. But I think from your accent and your origin, you are from Munich or from Bavaria, are you not, Rupert? Yeah,
that's right.
Yeah, and so then after a postdoc internship and assistant professorship at Princeton, which in 2013, he became professor at Caltech, and in 2016 also professor at LMU Munich. Thank you for your availability. I know it's late in LA and it's a great pleasure to have you. And Professor Frank, please start.
All right. Well, thank you very much. Do you want to record this or?
It's recorded already.
Oh, we're already recording. Okay. So I should have been careful what I said. All right. Well, anyway, so welcome everybody. Thanks for joining. Thank you very much for the invitation. It's a pleasure to speak here. And the topic of my talk will be a blow-up of solutions of a certain type of critical elliptic equations in 3 dimensions. And I have to warn you that this is a little bit of a technical talk. I will try to go as slow as possible. I will include a lot of background, and essentially my goal will be to explain our result. I will have probably very little time to go into any details of the proof, but there I refer you to the papers, which are all available on the archive and which are all joint work together with Tobias König from Paris and Hynek Kovarik from Prussia. Okay, so let's get started. Let me explain you what we mean by the title. Just let's go through these words that appear there. What do critical equations mean and what does blow up mean? And actually, at the beginning, I'm going to focus on general dimensions, and only later I will talk about the specifics in 3 dimensions. All right, so here's the first slide, which has the equation, the PDE of interest, and also the minimization problem that we will be interested in. Okay, so the whole talk, I will jump back and forth between behavior of solutions to this PDE and behavior of minimizers of this minimization problems. And as I will tell you, there's a close relation between the two, but there are also certain differences. So let's look at this in more detail. So the dimension will be noted by capital N. And this will always be greater or equal than 3, so that we have a Sobolev inequality valid. And then we always take an open bounded set in Rn, typically with smooth boundary. And the things that we are interested in are either PDE solutions. So this is minus Laplacian u equal to u to a certain power. And then that's not the full equation, but there will be some lower order terms. And I will be much more precise later. So, but let's, for the moment, just look at this as a perturbation of where you have the pure power nonlinearity. We're always going to be interested in positive solutions to this equation, which satisfy Dirichlet boundary conditions on the boundary of the set. Okay, and the other type of problem is where you try to minimize the integral of the gradient of u squared, again, perhaps perturbed by some lower order terms, and you minimize that under a given LP norm where P has, again, a very special value. And when you look at this, you see that the value that you find here, this is exactly this value minus 1. Put differently, this equation here is sort of the Euler-Lagrange equation that corresponds to minimizers for that problem. That's the relation. Okay, so minimizers of this problem here, which typically turn out to be positive, okay, are solutions of this problem. So when we say we study minimizers of the problem, you can think we're looking at a special class of solutions of this equation. Now, what I was saying is I was emphasizing the role of these exponents, and that's really special. Okay, this is the power where this LP norm downstairs scales exactly in the same way as this gradient norm upstairs. Okay, this is called the scaling critical, and they're both in the minimization problem and in the equation. And the significance is because this power is scaling critical, you have an embedding which is not compact. Okay, so when you have functions, a sequence of functions that converges weakly in H1, it does not necessarily converge strongly in this LP space with a critical exponent. Now that's at first sight a mathematical curiosity, right? I mean, sometimes embeddings are valid, sometimes then they're compact, sometimes they're not. But the point is that this problem, which is special from the point of view of mathematics, is also very important in applications. Both in physics, you have such equations appearing. For instance, in 4 dimensions, when you have a cubic nonlinearity, which is a power 4 in the functional, or in geometry, where you have, for instance, the Yamabe problem, which is a certain problem of this type. And there are many other problems. I don't want to go into particular instances, but I think these applications really sparked a lot of the interest and why people have studied this in so much detail. Now, the point is, when you don't have any perturbation, right, then this equation does not have a solution if the set here is not the whole space. And now, what you are interested in are situations where these perturbations, these lower order terms here, depend on a certain parameter. When this parameter is positive, you do have a solution, but as this parameter disappears, then the solution disappears. What does it mean that the solution disappears? Well, it means that it converges weakly to zero. And now let's remember, we said that the specific property of this equation is that this embedding is not compact. All right, so the solution does not necessarily converge strongly to zero in this LP space. And actually in all these applications, it does not. And actually what does happen is a so-called blow-up phenomenon. And this is what we're going to study. So in other words, what this weak convergence to zero means more concretely in, I mean, when you look at the functions and let's describe their limiting behavior. Let me be a little bit more concrete and turn to one specific such problem. And this has been studied a long time ago. So I'm going to talk now in this slide and the next couple of slides to some works that really date back 40 years. And so there's a fundamental paper by Bricis and Nirenberg where they studied such equations. I should say that really the Yamabe problem was studied around the time and actually earlier. And this has somehow, this problem gained interest as the Yamabe problem sort of stripped off of the geometric part where you have the analytic part in a more pure form. Anyway, so the lower order terms here for the equations are just a linear term multiplied by a given function v, which we assume to be bounded. In the functional, this means that we have a quadratic term v times u squared that we add here. The minimization problem, as I said before, you want to minimize this gradient u squared plus vu squared under fixed LP norm. And you're going to call this minimum, or infimum, I should rather say, you should call that SV. Good. And as I said also before, one thing that minimizers do is they solve this equation. So if you're interested in solving this equation, and I mean, more precisely, this whole problem, right, with the positivity condition and the boundary condition, then you might try to solve this minimization problem. And then the question you have is, the first question you have is, do there exist minimizers? And again, this is a non-trivial question because of this lack of compactness that I was talking about, right? Because so if you would have a different exponent, a smaller exponent down here, then that would be a triviality. You would have immediately existence of minimizers. With this exponent, it is not. So the first problem that we want to investigate, or that Brice and Nirenberg wanted to investigate, is when do we have minimizers for this problem? And in order to state the result, let's introduce a bit of notation, namely by S without a subscript, I mean the optimal Sobolev constant. In other words, that's this thing here, this minimum, however, where I replace omega by the whole space and where I drop the V term. That's a Sobolev inequality that you get, and S is its best constant. And using this, we can formulate the problem of whether, we can characterize the question whether this infimum SV is attained completely. In dimension 4 and higher, you have an equivalence that this infimum is attained if and only if this infimum here, the numerical value of this infimum, is strictly smaller than the Sobolev constant. And in fact, that the same thing is true in 3 dimensions as well. This, you should think this is good news, because so the existence of minimizers, which is sort of a complicated thing about whether you have a function, is reduced to essentially a computation. I mean, why do I say computation? Well, you have to come up with a function u, you have to guess a function u, such that when you plug in and when you compute this quotient, then what you get is strictly smaller than the Sobolev constant. So that's fine. It's of course somehow not really the answer that we want at the end, because what we do want at the end is given our V, we want to read off, is there optimizer, is there no optimizer? So that's where, very importantly, a distinction between that case of dimension greater than 4 and the case of dimension equal to 3 appears. In this existence of optimizer, immediately when the infimum, the essential infimum of this function V is negative. Okay. Whereas in 3 dimensions, you need to build a certain quantity, which is called phi of V, and which I'll define on the next slide. And then you have to look at this function and again answer whether this thing is negative. Okay, so even though it looks similar, I mean, it's the negativity of a certain quantity, actually this phi V is quite different from the V. And why is it different? Well, the point is that in dimensions 4 and higher, this is a local thing, right? You just have your function V and you look at each different value. And if this value happens to be negative somewhere, then you have a minimizer and everything is fine. In order to get the phi V, you need to do the following. First of all, you need to compute the Green's function of this minus Laplacian plus V. That's a linear operator considered with Dirichlet boundary conditions. Okay, so the Green's function, that's a function of x and y. Now you know that this function blows up as x equal to y, and you know exactly how it blows up. And it blows up like the fundamental solution in all of space. And then what you do is you subtract off this singular term. And then once you have extracted off the singularity, then actually you know that you can pass to the limit x equal to y. And this is then finally your function phi of v up to a minus sign and a normalization constant. Okay, so what I want to emphasize is this is a very non-local quantity. If you change V at some point, then the Green's function changes everywhere. Okay, it's also a quantity that cannot so easily be controlled because you have this limit involved, and it's a quite what should I say? I mean, it's non-local and an involved thing which well, which characterizes this. But I mean, the point is it's an equivalence. So you cannot get, I mean, you can't do anything about it. That's just the nature of the problem. Okay, you have to deal with it. But the message is 3 dimensions is completely different from 4 dimensions and higher. Now, this might remind some of you of Rick Shane's solution of the final solution of the Yamabe problem. There, in the Yamabe problem, you have a difference in dimensions starting from dimension 6. Okay, so that's because of an extra cancellation that happens there. And then their things are again different or sort of simpler when you have dimension 6 and higher, and they're harder in smaller dimensions. That's a similar thing. And also the trial function that Shane used there is rather similar in spirit to such a quantity. Such a quantity is sort of, I mean, morally similar to this effective mass. And another relation, if you're familiar from this geometric analysis background, then the existence of a minimizer under the condition that you have a strict inequality that's due to Aubin. And perhaps the last thing that I should say is that while the main parts of this theorem were completed by 85, actually the last equivalence between 3 and 2, that's due to Drouet about 20 years ago. I should also say a little caveat at this point. I have told you that if we have a minimizer, then we have a solution. And then I've told you that sometimes you don't have a minimizer, right? Which is, I mean, implicit in this theorem. Now, if you don't have a minimizer, that does not mean that you don't have a solution, okay? There could be solutions that are not minimizing. However, number one, in this talk, we will be mostly interested in solutions that are obtained by minimization. And number two, actually, you can prove under various assumptions that sometimes you don't have solutions to the equation, even not minimizing, okay? Or sometimes you can prove existence of solution. So that does not completely solve the problem by no means, but at least it's a good start, and at least the problem of these energy minimizing solutions, that's completely solved by this. Okay. Let me move on. I should say that, I mean, this is all a review of things that are probably well known to quite a number of you. If there are any questions or anything, please feel free to interrupt me and ask. All right, so what are we gonna do now? So we're gonna specify V now to be a negative constant, and moreover, to be a small negative constant. So it's just minus epsilon. And then the equation that we have is, well, that's what it is, okay? Perturbed by this epsilon times u epsilon, everything else is the same. And put differently, I mean, we're looking now at solutions of this problem, and not an arbitrary solutions, but we want to have solutions which this energy, sort of, you can put this or you cannot put this, tends to the value of the Sobolev constant. Let's go back. Let's think what we know so far. We know that this potential is negative somewhere. So therefore, we know that there exists solution for any arbitrarily small epsilon. Moreover, it's easy to see that the solutions converge weakly to 0 in H1. That essentially follows also from the fact that I told you, namely that you don't have solutions for the limiting problem. And then if you think a little bit harder, you notice that if you look at this quantity, what you have down there, this is essentially normalized. It's this integral down there hardly depends on epsilon. And then you see that this converges in the sense of measure to a Dirac delta. Okay, that's this blow up. So these things are rather easy to see. And then we're now about in the year 1989. People asked the question, can one describe the behavior of the solution in more detail? In other words, instead of just saying this thing here should converge in the sense of measures to a delta function, we want to blow up, we want to look at a neighborhood of this point and see how this limit is approached. And yes, this can be done. And there are initial works by Butt and Atkinson. Then there's a very important paper by Bricis and Pelletier. What they did is they studied the radial case. And also, rather importantly, they made three conjectures, three very precise conjectures about how these solutions should look like. And they proved these conjectures in the radial case. And then about a year or two later, in two separate papers, Hahn and Ray solved first two conjectures of Bricis and Pelletier. I will not write down the complete answer. That would be rather technical, and you will see some details a bit later. Anyway, so that's the first result in this direction. And whoops, and I mean, there's one thing I wrote at the very top, but which I didn't stress. The most important thing here, this is dimension 4, right? And where do we use dimension 4? Well, that we do use in order to say that solutions do exist for all epsilon, down to epsilon equal to 0. That was the criterion that we had in dimensions 4 and higher. Let's move on. Let's talk about the second problem. The second problem is the corresponding minimization problem. So same thing, right? This is the functional that seen before in the case where v is equal to minus epsilon. We're going to minimize this. We know from Bricis-Nirenberg that we have minimizers for all epsilon. We know that we converge weakly to 0. And again, we can ask the question, can we describe the behavior of the minimizers in more detail? Now, at this point, you might say, well, minimizers are solutions, so we don't ask actually anything new. Well, that is right, but the question is, can we distinguish these minimizing solutions from the general solutions that we have seen before? Okay, so we can ask more precise questions. And again, the answer is yes. And this, or to be precise, in a very closely related problem, was solved by Yunjae Wei in probably also the early 90s in dimension n greater or equal than 4, and then exactly in this version by Takahashi. And we also had a paper where we generalize this slightly and prove a little bit more refined questions. So the summary of the last two slides is we get a rather complete answer to this question in dimensions 4 and higher. The natural question, the question that is the main focus of my talk, is what happens if we now go to n equal to 3? Where we've seen from the work of Bricis-Nirenberg that the situation is different, right? And actually, the paper of Bricis-Pelletier from 1989 does have a conjecture about this. And this conjecture, as far as we know, has not been discussed so far in the literature. And what I'm going to show you is essentially a proof of this conjecture and some additional questions around that conjecture. But now the first thing that we need to talk about is how do we set up the problem? Right? Because before, the point was we had a solution down to epsilon equal to 0, and then we had non-existence. Now, when we are in 3 dimensions, the solution stops existing already at some positive value of epsilon. So let's put this into a somewhat different framework. And in particular, we can treat a slightly more general problem. So I want to tell you what so-called critical potentials are. So this is a function that's defined on and is continuous on the closure of our domain. And remember what SA was. SA was this minimization problem, right? Where we have upstairs, I mean, there you see it up here. Upstairs, you have A times U squared. And so you want to have a potential, we call it potential critical, is that if you have exactly that potential, then you get the Sobolev constant. What we always, perhaps I should say this, I mean, in the intuition is always that A is somehow negative. Okay, but the thing is, from Bressis and Nirenberg, we know that in 3 dimensions, you really need to be significantly negative in order to go down below the Sobolev constant. So a critical potential is one which is not strong enough to push the infimum below the Sobolev constant. However, when you make the function only a tiny bit more negative, right? So that's the A tilde, which is less or equal than A, but more negative. Then you go down below the Sobolev constant. Does that make sense? Okay. So this is the thing, I mean, that you might, I mean, if you go up to that problem, right? So this, let's look at the simplest case where V is a constant. In 4 dimensions, this infimum will always be strictly below the Sobolev constant. That's a consequence of this, let me go back, consequence of this thing here. Whatever potential you take, if it's negative, then you're always below the Sobolev constant. In 3 dimensions, this might not be the case. Anyway, what you do see is that such a minimum is monotone in epsilon. So at some critical epsilon, which is strictly negative, which isn't, I mean, strictly positive, so minus epsilon is strictly negative and not equal to 0, you already reach the Sobolev constant. And that, with that particular value, that particular constant, that would be critical. That would be an example of a critical A in that sense. All right, and now the problem that we're interested in, so from now on, the dimension is equal to 3. The A is a critical thing, and we're looking at this problem. Minus Laplacian u equal to 3u to the 5 minus A plus epsilon VU. So you see, I'm writing it as something critical plus a small perturbation. And by criticality, at least if V is non-negative and not identically 0, we know that the solution exists up to epsilon equal to 0, and there it stops existing. And that's the case now that we want to investigate. You also see that I smuggled in a factor of 3 there, which was not there before, but that's just a normalization which makes the formulas appear a bit nicer. You can just absorb the 3 into the u, so that's nothing. And then the other thing is, I mean, there are many solutions to this equation, probably. We're looking at a particular class of solutions, namely such solutions whose energy is close to the critical Sobolev constant. This is problem number 1. Problem number 1 is, what can we say about such solutions? Problem number 2, very similar. You look at this minimization problem, and right, for each positive value of epsilon, you have typically, if V is nice or negative, you have a minimizer. And now again, you look at this family of functions, u epsilon, which exists for every epsilon, and you ask yourself, what happens if epsilon goes to 0? All right. And again, I should say that minimizers here are particular solutions of this problem, which also satisfy this limiting condition. But for minimizers, we may ask different questions. Now, I'm going to tell you the main result, at least in a simplified version. because it's going to be a bit technical and we need to introduce quite a lot of notations to really get to the precise statement. So I'm going to tell you now what's happening. I tell you the answer, how these functions u epsilon from the previous slide, how they do behave. Okay, so let's look at such a family of solutions. Assertion number one is there is a concentration point x naught. This concentration point is inside the domain, not on its boundary. If you stay away from the concentration point, say for the moment, let's stay order 1 away from the concentration point, then the solution goes to 0 in a strong sense. If you are at or close to the concentration point in a sense to be made precise, then the function tends to infinity. And now let's say this in more detail. There is a certain localization length, which will be lambda epsilon to the -1. And for all practical purposes, you can think of this localization length as being epsilon. And so one thing is, if you stay away from the localization point, order 1 away, then your function, your solution, looks like the Green's function. This is the Green's function with pole at the concentration point and of a size square root of epsilon. Okay, that's what I mean. It tends to 0. That's made more precise here. Actually, it's of order square root of epsilon. And if you remove that square root of epsilon factor, it has a very nice On the other hand, if you are close to the concentration point, and what does that mean? Well, that means now you have to be a little bit careful. So there are certain points which do converge to the concentration point. If you are within order epsilon at these concentration points, then your solution u looks like exactly this function. All to the power 1/2, right? That's a function that many of you will recognize as the optimizer of the Sobolev inequality. I want to stress, for those who have not seen the function before, this is a function that lives on the scale 1 over lambda epsilon, and which has the typical size lambda epsilon to the 1/2. Put differently, the function lives on a scale epsilon and has a size epsilon to the -1/2. Okay, so outside we're epsilon to the 1/2, at the singularity we're epsilon to the -1/2, and then there's a length scale epsilon that separates the global regime from the localized regime. And a reason why this problem is hard is when you do a rough back of the envelope computation, what you will find is that you have a localization length epsilon squared and a maximum epsilon to the -1. This is not what you have, right? I told you the localization length is epsilon, which is much larger, which is much smaller. Okay, so the function is somehow more spread out and smaller than what you would naively expect. And why is that so? Why is that back of the envelope computation wrong? Well, it is wrong because it does not take this phenomenon of criticality properly into account, because there is a certain cancellation. And that cancellation is really what makes this problem difficult, and why you have to work to much higher precision than you would expect, and why you need a much more precise statement than just such, I mean, I didn't make any precise statement at all, but I just tried to give you an intuition. But really you need to extract a couple of lower order terms here to make precise how u looks like close to the concentration point. Okay, but I hope, I mean, I still wanted to give you that slide and tell you what to expect. So you're square root of epsilon away and then you're 1 over square root of epsilon at the concentration point with a transition region of order epsilon. And again, you see a cancellation, which makes the usual computation go wrong. So now I have about 10 minutes left, and I'm going to be now a little bit more precise. I'm going to introduce definitions for 2 slides, where I introduce the objects that you need to understand our main theorem. And then I will conclude with a couple of general remarks about this theorem. So at the beginning, let me introduce here, remind you that GB is the Green's function of minus Laplacian plus B. I'm writing B because B will be either A or will be 0. So if I write B, it can be either. We have already seen that object, the Green's function minus the standard singularity. That's a regular part of the Green's function. We call that HB. And then we've also already seen phi b, that's the diagonal value of the regular part of the Green's function. And then I remind you of this theorem of Brécis and Drouet, which says that because we are critical, this function is non-negative. So phi a is non-negative and actually has a minimum at 0. Has the minimal value 0. Okay, good. So now I'm ready to state the assumptions under which we're working. There, I go quickly through some standard assumptions. I told you boundedness. I told you that the boundary should not be too bad. The functions should also be reasonable, both a and v. Probably if you would work harder, you could reduce these assumptions. That was not the goal of our paper. Then I also already told you that A is a critical potential, right, in the sense of Hebet-Végot that we discussed, meaning that the infimum is exactly the Sobolev constant. Now we come to the 2 important assumptions. The first assumption is that the function A has to be negative on the set where phi a is equal to 0. Okay, let's remember this. The set phi a, this was the special set from the Brécis-Drouet theorem. This is the set where this minimum is attained. That's a special set that will play an important role. What one can show, this is not very hard, is that A is always non-positive on that set. The new assumption that we impose is that A is strictly negative. You should not worry too much about this assumption, in particular when you assume that A is a constant, which is, by the way, the assumption that under which Brécis and Pelletier formulate their conjecture. So when A is a negative constant, this is not really an assumption. In general, while you have this, anyway, you have this less or equal than 0, you require strictly less than 0. There's another assumption that we have here, which is a non-degeneracy assumption. So once again, the function phi a attains its minimal value 0. Gradient of phi a is 0. Under these assumptions on A, the function phi a is C2, so we can talk about its Hessian, and what we want is that this minimum is actually non-degenerate. So the Hessian should, which is non-negative, should actually be positive definite. We believe that this assumption F is generically true. We did not investigate this. We did not prove this. I know that people proved similar things when A is equal to 0. It's a bit different, but I would think that one can really prove some genericity here. Another reassuring thing is that if you go to the simplest case where omega is a ball and where A is a constant, this is the original Brécis-Pelletier setting, then this assumption is verified just by explicit computation. So, okay, so these are our assumptions. So I hope you agree that none of this is very severe. Last piece of notation, and we're ready to look at the first theorem. Here's the function, again, that is a minimizer in the Sobolev inequality, or equivalently a solution of this Euler-Lagrange equation on all of R3. Here's the equation. And here you see I put the 3 there to have a nice form of the solution. Okay, that function is supported everywhere on R3. We want to work in H10. So what you do is you project this object here onto H10 space, or if you want to do it more concretely, you can solve the PDE that the Laplacian of this thing is equal to the Laplacian of u, which is minus 3u5, and you're equal to 0 on the boundary. Such a solution exists, and we're going to call that Pu, where x is the point where the function is localized. 1 over lambda is the length on which it varies. In space, which is sort of the space of symmetries of the Sobolev inequality. So it's the space generated by the function itself, the space when you vary with respect to lambda, and when you vary with respect to the x coordinates. So that's a 5-dimensional space, and you project orthogonally in H10 with respect to that inner product to define a projection operator pi. I know that's a lot to digest. It's not terribly important. I just want to have it written out. Here's the first theorem. Okay, so once again, we look at a family of solutions to our equation which satisfies this energy minimality condition. Perhaps it's worth going back just to this, that you see it once again. Here's the equation that's star, right? Critical exponent, critical potential, low order perturbation, satisfying an energy minimality condition. Here we are back at the theorem. The statement is, you can decompose the solution as this Pu function that we looked at before, minus a term which involves these regular parts of the Green's functions, but then projected away from this funny space that we've seen before and multiplied by a small factor. And then there's a remainder, and the remainder is small in H1. All right, so let's go through this again. Remember that those are called standard bubbles. They have 2 parameters. X epsilon, that's the parameter where the bubble sits. Lambda epsilon is the inverse localization length. What I'm saying is that, well, these points converge to point x naught. And the point x naught, at this point, the Robin function vanishes. And moreover, this function, which is a function you build out of V and the Green's function, is negative. And then this is the formula for the localization length. And everything is multiplied by a factor that tends to 1. I want to go to this, which is perhaps a little bit, this is a corollary, which is a little bit more intuitive, perhaps. This is what I told you already. Away from the concentration points, you look like the Green's function. At the concentration points, the function is of order epsilon to the minus 1/2. All right, now I'm running out of time, so let me perhaps tell you that this theorem, first of all, that this thing proves the Brécis-Pelletier conjecture, except, we prove the Brécis-Pelletier conjecture in the same paper. This is the translation of the Brécis-Pelletier conjecture to that problem, but that's a minor detail, and I refer you to our paper. The thing that I wanted to say is that our result is best possible in the following sense, that about this function, this concentration point x naught, you cannot say anything else than what we said in the theorem, namely that it is a point where the Robin function vanishes, because for any such point you can find a solution. What we show in some sense is the optimality also of their result. Okay, so every solution really concentrates at these points. I will skip these two open questions. You can look at those on the slide on the web page. And I want to go now to the theorem about energy quasi-minimizers. So the long and short of it is that if you have a minimizing solution, then the point x naught is not an arbitrary point, but it is a point where a certain quantity, look at this quotient here, qv squared divided by absolute A, where this quantity is maximal. So we can say the point x naught, I mean, not only the previous theorem told us that the point x naught lies in this set, but this set could be large, and the minimizing points are precisely those where this quantity is maximal. So that characterizes these points. And I should say, the theorem does more. The theorem, two things more, okay? The theorem, first of all, is valid not only for minimizers, but for functions whose energy is close to the minimal energy, which is a quite large class. And when you look at perturbations of the equation, say time-dependent equations, then this is really a theorem that you need, where you only have energy information at time 0, and then you get a structure result at later times. That was the first point. The second point is we can also compute the leading order behavior of the minimal energy. You find exactly this supremum appearing, which characterizes the localization of the point. And you see here that this thing here, this expansion of the energy, starts with the term epsilon squared. And the fact that there is no term epsilon, that's exactly Drouillet's theorem, namely that A critical implies that the infimum of phi A is equal to 0. So you can think of this as that we go one step further in the expansion. And so I had prepared more slides that I'm going to skip. I tried to explain you a little bit about the proof. I go immediately to the summary. I'm sorry that I couldn't tell you a little bit more about the difficulty. I just mentioned it here on this very last slide. I told you that we could prove this conjecture by Brécis and Pelletier, which describes in detail how solutions of these equations blow up. And the specific feature is in that in 3 dimensions, you need a notion of criticality of the lower order term. That notion of criticality leads to a certain cancellation property, which we see, for instance, in the energy asymptotics by making a term that's usually non-zero equal to 0. You see it on the length scale of the optimizers, where the functions now are much more spread out and much flatter. And results, I mean, so this cancellation property is the main thing you have to deal with in your proof. And other things are some of the two-scale structure that I mentioned. I said that you have a globally of a size globally of a size square root of epsilon. Locally close to the concentration point, you have a size 1 square root of epsilon. So you have these two scales, the small scale, local scale, and the global scale. You have these two scales, and then you have a certain lack of coercivity of a linearization that I did not have time to discuss. A very important thing is way of how to get around this is using orthogonality conditions. And so you have these parameters at your disposal. If you remember, there was a parameter alpha, there was a parameter lambda, there were parameters x, x1, x2, x3. These are 5 parameters. Somehow, because by choosing these 5 parameters, you can have 5 orthogonality conditions satisfied, and this helps you a lot to deal with these problems that you have. This analysis is most easily carried out in H1. That's perhaps a little bit surprising for experts. In recent years, there has been great progress by Drouillet, Hébert, Robert for L-infinity analysis. On the other side, also Rick Shane and Brandle Marquez have worked on compactness issues, this was mostly an L infinity analysis. We go back to the very basic, I should say, H1 analysis, because that's what sort of, at least to our mind, can better handle these two-scale structures and these orthogonality conditions, which we need. Anyway, that's all I could tell you in this. I would invite you to have a look at the papers for more details, or please ask me questions. I would like to thank you very much for your attention. Thank you.
Thank you so much, Rupert, for this very interesting talk. So a question to the audience. Are there any questions, please? If you have, then raise the hand and I will give you then the permission to speak on the Zoom webinar. Okay, there was coming a positive feedback from Julie Kladabak for the very clear talk.
Thank you.
Any other questions or comments? Well, I have a question to this orthogonal space. So, okay, you take the bubble and then you later you look actually for the firstly the Dirichlet solution, basically when the right-hand side is the bubble, and then later you took also the partial derivatives. So why do you have to take the partial derivatives with respect to x1, x2, x3? So intuitively with respect to lambda, I understand, but why with respect to the other coordinates in order to choose? Or how did you find actually this orthogonal projection?
So thank you. And I understand that I really didn't explain many things that are that I tried to say here, and sorry for that. It was very, very fast. I should mention two works by one work by Bari and Coron, where they initiated a lot of this analysis, and then in particular also the work of Ray. And in particular in these works, somehow they dealt already with these orthogonality conditions. It's a somewhat different situation, or somehow we need to go into more precision. The intuitive reason is simply you have, let me see, I mean, you have essentially the 5-parameter family of Sobolev optimizers. They're parameterized by 3 spatial parameters, that just where you sit. Then you have one length scale, which says how much you're spread out. And then at least when you have the homogeneous version of the Sobolev quotient, you can also just simply multiply the solution by a number. Okay, so these are kind of 5 trivial invariances. And those are reflected here when I look at the first term. The bubble, right, has the x parameter, the lambda parameter, and the alpha parameter. These are exactly, if somehow the parameters, if you don't have an orthogonality condition, then you can slightly move the bubble, or spread it out or contract it, or multiply by a constant, so in order to achieve the orthogonality. Okay, so you somehow you just adjust the bubble in sort of an optimal way. Put differently, you minimize the distance between your function u epsilon and the 5-dimensional manifold spanned by alpha times pu x lambda. Okay, so it's a 5-dimensional manifold. You project onto that manifold, so therefore you have 5 orthogonality conditions. I mean, your orthogonal to the tangent space is 5-dimensional, and you're orthogonal to the tangent space at the point of projection.
I see,
and
I see.
This gives you
I
5
see.
parameters.
That is why the 5 parameters are.
So,
okay, yeah, that is clear. Yeah.
Yes. So this is sort of, I mean, it's sort of natural that you get these 5 parameters. What is where you really have to work then is to say, when you do minimization, then, well, you try to minimize. I mean, you try to make things as good as they can be. That's not what I want to talk about. I want to talk about solutions. what we use is really a lot of Poiseuille identities. And these Poiseuille identities come exactly from these 5 parameters that are free. Okay, so each parameter, again, the parameters that you freeze in the first step to project kind of appear later on, and actually twice, each in terms of a Poiseuille identity. And so you have 5 Poiseuille identities coming exactly from these spatial variations, from the contraction expansion, and from the multiplication by constant. So you use them, the invariants under these 5 parameters, first to get the standard bubble, then you use it to get the first term, and then you use them again to get the more precise localization. So you found exactly the point. I mean, it's exactly these 5 parameters and these 5 orthogonality which correspond to these 5 orthogonality conditions that you have to use over and over again, and somehow not be frustrated if you have already used them. They just keep on using them and use them more precisely at each step.
Very interesting. Okay, so I think, there's still maybe one question is possible maybe? Are there any other questions by the audience, please? Well, if not, each of you received an email to a coffee break. Rupert said he cannot join too long, but maybe a few minutes. This would be very nice. And please join us to the coffee break. And thank you again. Let's join me again to thank Professor Frank. And I hope to see you all to the next talk. Okay, thank you. Bye, guys.
Thank you. Bye-bye. Thank you.